Good morning, students. Welcome to the mass transfer course. Today will be lecture 17. Here we are discussing about the interphase mass transfer. In interphase mass transfer, we have understand the basic concepts. Means there will be two phases in direct contact. There will be two boundary layers. One is from G phase, another is from L phase, and there will be interface. Thereafter, we have calculated overall mass transfer coefficients based on one is based on gas phase or G phase, and another is based on L phase or liquid phase. Here I am telling you repeatedly, although we are taking the example of gas phase and liquid phase, okay, but it will be applicable for any two phases. So in generic term, we can, instead of telling gas phase, liquid phase, we can tell it G phase and L phase. G phase and L phase, it can be gas liquid, it can be solid liquid, it can be liquid liquid, it can be gas solid. Any two phases to make this interphase mass transfer, then these concepts will be applicable to it. And thereafter we solved three problems. And here one interesting thing is we have to identify which phase has a higher resistance, means which phase is controlling the mass transfer. Because if you identify this one, then we will try to reduce the resistance so that mass transfer will be high, means we will get the high flux. High flux means we will get the better separation in a small. So still now what we have discussed, these are the fundamental of mass transfer. Now slowly we will move at how this fundamental of mass transfer can be applied in designing the equipments. Because I have to design as chemical engineer, my role is to design the equipment so that I will get the separation. So let's start the design aspects of the mass transfer equipment from the understanding of the fundamental of mass transfers. So if you see that equipments will be generally four types based on its flow pattern. Okay. First one is steady state counter current mass transfer. See, I told already, always we will design the equipments under steady state, because chemical plants will run in continuous mode with steady state. It will run 330 days for continuous mode, then remaining 35 days it will be for maintenance shutdown, then again it will be plant will start and it will run for 365 days. And mass transfer equipments are generally operates under steady state condition. That's why we will focus on designing the equipment steady state. So that is one is counter current mass transfer. You know this counter current. So G phase is flowing one direction and L phase will flow in other direction. Then steady state co-current. Co-current means in which direction G phase will flow, L phase also will flow in same direction, that is co-current. Cross current means, let's check, G phase is flowing north to east, okay, then L phase will flow east to west, that is cross current. I'll come this thing later. Then steady state mass transfer in stage-wise contact of two phases. Stage-wise contact means we have taken the example of distillation. There will be in the equipments multiple stages will be there, so that we will get the better solution. So in general there are 4 categories in terms of flow pattern. So first two pattern, co-current and counter current flow pattern, generally we use the packed bed. In packed bed there will be some packing material. G phase will flow in one direction and L phase will flow other direction, that is counter current. If both will flow in same direction, this is co-current. And cross current generally used in liquid extraction. So there is one phase will flow in north to east and another flow will flow from north, one phase will flow north to south and another phase will flow east to west. Generally in liquid extraction this type of cross current mass transfer movements are used, and generally in distillation stage-wide contact equipments are used. So there are 4 categories of mass transfer equipments in terms of flow pattern are available, and we will discuss these 4 types one by one. Today we will discuss about only the counter current mass transfer, first one. Okay. So if you take the counter current mass transfer, so let's take this is one equipment, and in this the packing material will be available. Sometime it will not be packing material. Let's say this is my equipment, and I am giving the nomenclature. Bottom is 1, top is 2. So always use this nomenclature, and because all the equation will be based on this equation. So bottom is 1 nomenclature and top is 2. Here L phase is heavier phase and flows down the apparatus. So L phase is coming from the top to bottom, okay, and G phase is lighter phase and flows up. G phase is going from bottom to top. If you take let's take the example of absorption of ammonia in water. So ammonia in gas mixture, this is the lighter phase, so it will flow from bottom to top, and your water will flow from top to bottom. And G and L phase are mutually immiscible. So you have to remember that these 2 phases should be immiscible to each other. And solute A, in this case ammonia, will transfer from one phase to another phase. In this case, if you take the example of absorption of ammonia from the gas mixture into water, the solute is ammonia, it is transferring from gas phase to liquid phase. Phases can be gas liquid, gas solid, solid liquid, or liquid. Although I am telling repeatedly, although I am giving some example based on gas to understand it. Absorption, ammonia absorption, I am giving the example, but it will be applicable to other cases also. So in general, if you take the G phase and L phase. Okay. So nomenclature is bottom is 1 and top is 2. Now if you take this thing in some better way, okay. Now what we have given the nomenclature? So 1, this is 2. Now what is G1? G1 is the rate of input of G phase at section A. Section A, that is what is the rate of input, that is moles per time. Whatever the G1, whatever G2, G2 is rate of output of phase G at section 2, the unit will be moles per time. So what is the total flow rate? G1 at section 1 and G2 is the flow rate at section 2, and corresponding mole fraction small y1 and capital Y. Okay. Now here I am expressing, and another thing I am taking, this is the extreme point. This what is input, this is output, but what is happening, there will be some change in the, and if you take, let's take whatever, ammonia, absorption of ammonia. So whatever ammonia is there, okay, let's take 10% ammonia is there. 10% means, let's take totally, if 100 mole, 10 mole ammonia and 90 mole is your air. So ammonia is getting absorbed from G phase to L phase. So when it is going up, okay, then ammonia content will decrease. That means here it is entering 100 moles per second, let's take. So here will be, let's take 2 mole is transfer from gas phase to. So in this, here will be 98 moles. Here will be 95 moles. And if let's take G2 y2 equal to 0, means all ammonia absorbed, so here will be 90 moles, because 10 moles ammonia is absorbed from this to this place. So here G phase is changing, total flow rate. You understand this, what I am telling? Let's take G phase is entering 100 moles per second, okay, and y1 equal to 0.1. So in this and here y2 equal to, let's take y2 equal to 0, means 100 all ammonia absorbed. So if this is the case, then here total flow rate 100 moles, y1 is 0.1, means ammonia is 10 moles, and remaining 90 moles are air, which is inert, which is not changing. 90 moles will flow from this place to this place. Now entering 100 moles, but some ammonia will transfer from gas phase to G phase. So here in this section, maybe that G will be, let's take 2 moles, so 98 moles per second. Two mole. Then here maybe the G is changing. Here maybe that, if 5 mole, then 95. And here maybe total G is, let's take 8 mole absorbed, then 92. Okay. And if all absorbed here, y2 means that G2 will be what? 90 mole is inert, because 90 mole is inert, means air which will not transfer from G phase to. So 90 mole will flow from here to here, but ammonia, as ammonia concentration, number of moles along this path is decreasing, so that gas flow rate G flow rate will keep changing along the equation. So if that's mean, that's why I have taken one in any place, okay, one point where my G gas flow rate is G, Y is Y, okay. So at any point, this is the gas flow rate and that corresponding concentration, isn't it? So keep it in mind here, gas G will keep changing from bottom to top. Similarly, L, let's say what is L? L1, L1, L2 will be rate of input, L2, this will be rate of input, L2 rate of input of phase L at section 2, that is moles per time and corresponding mole fraction x2. Now what will happen, that let's take x2 equal to 0, means pure liquid. So now ammonia is transferring from G phase to L phase. So L2, if L2, let's say L2 equal to 100 moles and it is 0. Now it will be, let's say 2 mole transfer here, so it will be 102 moles. Here 5 mole transfer, so here will be 105 moles. Here, sorry, 90 to 8 mole transfer, 108. Okay, so as whatever number of moles will transfer from G phase, so that will keep adding, and here as all these thing 10 mole transfer from G phase to L phase, so L1 will be 100 plus 10, 110 moles. So L1 is rate of output of L at section A. The nomenclature is based on section and corresponding mole fraction. Now what is GS? GS is rate of flow of G phase on solute free basis. Solute free basis means inert. If you take this is the 100 moles per second, Y1 ammonia is 10 moles, then remaining 90 moles, okay, that will be your GS, because it will not change. So if you take this one, so in this case your GS is 90 moles per. Isn't it? So total is 100 mole G1, among them GS 90 mole per second, that is the inert flow rate, okay, or it is called solute free basis, means it will not change. Air flow rate will not change because air is non-diffusing, it will not diffuse from G phase. So these 90 moles per, it will not change. So this is constant. So along this length GS is constant. Only thing is the ammonia is changing, that's why G will keep change, because if ammonia is transferring. So this is the constant term. So the G, this is constant. Because this is the inert flow rate, okay, and corresponding that mole ratio, that will be capital Y. Okay, so in this case, what will be Y? Okay, capital Y will be what? Moles of ammonia, that is 10 by 90. So this will be 1 by 9, slightly greater than 0.11. Okay, so this will be 1. Now Y1 will keep changing, but GS will not change. Which Y1 is, what is this? This is the mole ratio of ammonia, for ammonia, moles of ammonia by moles of, because this will not change, only how many moles of ammonia will transfer from G phase to L phase, accordingly this number will change. It will be 10, then 9, then 8, then 5, and accordingly that capital Y mole, this will change, but it is constant. But in this case this is also changing and this is also changing because it is based on total flow rate. Okay, and now I will show how this GS and capital Y1 is advantageous in calculation in designing the equipments. Because when I define the capital Y and mole ratio, some of you asked me, sir, why we need this one. So today I will try to justify you why it is required. But keep it, this thing is mine. In this case, G1 and Y1 both are changing. Here GS is constant, and if I express in terms of GS and capital Y, then GS is constant, capital Y will change. Okay. So if this is the thing, then corresponding in at any point the GS and capital Y and the top, it will be GS. This will be GS, it will not change because it is constant, it will be 90, and for Y2 that will be 0. If in this case small y is then 0 by 90, that will be 0 also. Okay. Similarly, LS is the inert flow rate. LS, rate of flow of phase L on solute flow basis. Solid flow basis means inert flow rate, which will not change. Okay, let's take if I put 100 moles per second water, okay, pure water, that means x2 equal to 0, ls will be 100. In this case, ls equal to 100, l2 also will be 100. But along the length, when it is transferring from let's take here to here, okay, so 2 moles transfer. So if ls equal to 100, then it will be 102, because here to here 2 mole transfer, so there will be 102. Okay, and here to here 3 mole transfer, then here will be 105. Okay, but LS, liquid flow rate, okay, water flow rate, it is not changing. 105, why it is coming? Because my ammonia is coming from this to this, so capital X2 is changing. Here capital X2 is 0, here it is keep changing. Similarly, when it is coming, that will be based on the total flow rate L1 and that corresponding mole fraction. LS will be 100, and corresponding what will be X? X will be here. In this case, you take the X, 10 mole is transferred from, because here 10 mole is ammonia transfer from this phase, so 10, because it is 100 to 90, so 10 mole transfer here, so 10 mole by what is L, LS, that is 100. Okay. So this will be my concentration. But what will be this? This will be 110 by 1 total number of moles. Total number of moles is 100 moles water plus 10 mole this will be X, but capital X will be this. Okay. So, and similarly, if I take in any position, because within this equipment it will keep changing, L is L this corresponding X, and LS is the inert flow rate or solute flow basis, and capital X, these are the things we have. Now what we know, y, capital Y equal to y in y by 1 minus y, x equal to x by 1 minus x. Now what will be GS? GS will be G by 1 plus capital Y, or G equal to GS into 1 plus capital Y. Similarly, L. Now let's see how it is coming. So this thing we have seen last day, how it is coming. Okay. So today we will take one example how these things are coming. Just for your simplicity. This is nothing but your simple material balance. So let's take, assume G, my gas flow rate, G is 100 moles per second. Now Y1, Y corresponding, so total is 100 moles G is 100 moles per this, and small y mole fraction, that is 10.1. So flow rate of solute will be what? 100 into 0.1, so 90 mole, 10 moles per second, and flow rate of inert gas will be remaining 100 by 100 into 0.9, so 90 moles per. So this is the inert flow. Now what will be capital Y? I have seen, this is the thing. Let's do it again. Y equal to capital Y by 1 minus small y. Capital Y equal to small y minus 1 minus small y. So 0.1 minus 0.1 minus 0.1, 0.1 by 0.5, so 1 by 9 equal to this. And if you take this definition, what is the Y? Y is what? Moles of A is 10 by 9, moles of B equal to 1 by 9. So if you see, and if you take this way, okay, same thing is coming. So 1 by 9 here also 1 by 10. Okay. Similarly, capital X will be small x by 1 minus small x. Now we told that G equal to GS into 1 plus capital Y. Okay, so G we know 100 moles. So let's calculate from this equation also. So GS equal to my 90, 1 equal to 1 plus Y equal to what? 1 by 9. So 1 by 9 equal to 10 by 9 into 10 moles. Okay, and flow rate of solute, what is GS into capital Y? Okay, what is the flow? That thing. So GS 90 into 1 by 9, 10 moles. See, here is also 10 moles, 10 moles is. And flow rate of inert GS into Y, this is equal to, ratio is 1 this by this. So if you take the denominator is 90 by 90, that will be 1, so this is 90. So it is coming. Okay, so this equation you should keep in mind. GS equal to capital G by 1 plus capital Y, or G equal to GS into 1 plus capital Y, and similarly for the L. But here the thing you have to keep in mind, GS and LS, these are the solute free basis or inert flow rate. This flow rate will not change. Okay, because this thing is not taking part in the mass transfer. Solute is changing. So whatever the change is going on based on the solute. That's why your total flow rate G and L, it will keep changing, but GS and LS will not change, it will be constant. Okay, so now let's take the material balance on this here. I will take the material balance on this under steady state condition. Under steady state condition equal to it, what is rate of input? Input is this and this, these two are entering, and outgoing is this and this. Okay, so if you take the component balance of solute, so then entering is LS. Let's take LS. I am making the material balance in terms of LS and corresponding capital X2. I will come later, L2 X2, that will come, and we will compare this, what are the advantages and disadvantages. So let's do first based on the solute free basis. So LS into X2 entering, and gas is entering. This I am taking here. Okay, any point here. So that will be your GS and capital Y. Okay, so I have taken the material balance, component balance based on this envelope 1. And what is output? Output is LS into X. This is output, and this is GS into Y. Okay, so at steady state this input will be output, so this will be this. So gs, now gs y minus y2 equal to ls x minus x2, isn't it? X minus x2. So y minus y2 by x minus x2 equal to ls by gs. Okay, so if you see this, now this is constant, this term, this is constant, because we know this is, and these are the constant term, it will not change along the equipment. What is the entering flow rate, outgoing flow rate will be same. Okay. So y minus y2, this minus this, and x minus x2, this is equal to ls. Now if I take the, consider the material balance for the whole equipment, this, so this will be same, and here instead of y it will be y1, here instead of x it will be x1, isn't it? So if you take this material balance for the equipment, whole equipment means this, so point 1 entering is this and this, entering is L2 ls x2 plus gs capital 1, and out is ls into capital X1 plus gs into x2. So if you take this balance, then y1 minus y2 minus by x1 minus x2, that will be ls by gs. It is same in this x2, because here we have taken the any point xy, this was this thing, now instead of this I am taking 1, so this will be y1 and x1, so same thing is happening, this is same, so y1 minus y2 divided by capital X1 minus x2 equal to this. Okay, now what is happened, now if you say take one equilibrium curve, so now we are making this thing based on the mole ratio, so that means you have to draw this equilibrium curve based on capital Y and capital X, because my calculation is based on my capital X capital Y. So if you have a, let's say, small x small y relation, so you have to convert this in terms of capital X capital Y. And you now you know how to convert, because in this first problem of what we have seen how to convert this thing. Okay, so first you draw this equilibrium curve which is required, always in mass transfer equipment that equilibrium curve is required. First your first xy, first your work will be to draw this equilibrium curve. Okay, now let's take this example as a absorption of ammonia from gas phase to liquid phase. If this is the case, then what is happening, y1 will be higher and y2 will be lower. Y1 will be higher, okay, capital Y1 will be higher and capital Y2 will be lower. So if it is a gas phase to liquid phase, so corresponding so capital Y is higher. Similarly, in this case here capital X1 will be higher and capital X2 will be lower, because ammonia is transferring from gas phase to liquid phase. So liquid phase here flow rate, what is X2, it will be lower, so it will increase this because ammonia is transferred from this. So y1 and x1 is higher, okay, 0.1. So let's take this is the 0.1. this is Q. So I know x1 and y1, I put it this point here. Okay, and what will be x2, y2? X2 will be in lower, because x2 y2 also low, y2 will be low. This is the point 2. Isn't it? So point 2 is whatever, this is the, because y2 is low and capital X2 low, so this is your y2 and the y2 and x2, and this is your x1 and this is your y. And if you draw now this line, what is this? You see, this is nothing but a your that this is the slope is y1 y1 minus y2 y1 minus y2 by x1 minus x2. So this slope your is ls by gs, which is based on your solid free basis. So if it is a solid free basis, means inert gas, so this line will be straight line, because ls, that slope will not change. So once you locate these 2 points, easily you can draw a straight line, and this will be the straight line, because here that slope will not change along the equipment. So this is the equipment, this is the point 1 and this is the point 2. Okay, now this line PQ, this line is called the operating line, and this line is your equilibrium line. Equilibrium line means, see, when you will reach to the equilibrium in this point, okay, then you don't, then mass transfer will not possible. Then that's when it reaches at equilibrium. But actually the equipment is operating in this line. It is away from the equilibrium, and if this gap, if this gas is higher, means you have a more driving force. You are away from the equilibrium, means you have better driving force, so then more flux will be there, isn't it? So because your if you see that this is the point 1 and this is point 2, and you know that slope ls by gs, and which is that's why, and it will not change, so that slope will be constant, okay, when p and u, and this is your equilibrium curve, and what is the gap between equilibrium curve and this operating curve, and that will give you the driving force. Okay, let's say this curve in far better way. So this is your equilibrium curve, this is my operating curve. Okay, so x1 y1, this is point 1 and this is point 2, and at any point, let's take m, that is x and y. Okay, so any point x1, whatever we have taken here, okay, x1 xy, so that will be in between some, isn't it? So this is your xy point, let's take x and y. Okay, and from this point, if you take the slope of minus kx ky, then it will reach to your m point, m dash point, and this will be your interfacial concentration, xi and yi. Okay, and this to this, if you go straight, so what is this distance? This to this, This is the driving force based on liquid phase. And if you take this to this, so this will be your M to N dash. This is the driving force based on the gas phase. Do you understand this one? So that's mean if your operating line is far away from your equilibrium line, if it is in, then your the driving force will increase. So if this point, if it is here, okay, so then your this gas phase driving force and liquid phase driving force will increase, and if it is closer to the equilibrium, then driving force will decrease, and then your separation will be difficult. So if gap between the operating line and equilibrium line increases, okay, then that you will get the easy separation, and if they are close, then separation will be. So when mass transfer is occurring from G phase to L phase, then operating line will be above the equilibrium. Okay, so what is the operating line? That is the above the equilibrium line, G phase to L phase when mass transfer. G phase means let's take ammonia is getting absorbed from gas mixture to water. Okay, now what will happen if the transfer takes place from L phase to G phase? Let's take stripping of carbon dioxide from the mixture of carbon dioxide ethanol, because you know we have taken the example that first we absorb the carbon dioxide from the mixture of nitrogen, hydrogen, carbon dioxide with ethanol. So that is one process, absorption. Then we strip off, means we make it heat it 60 degrees centigrade, then carbon dioxide is released from ethanol amine mixture to air. Okay, so how this, so in this case your liquid phase, if it is happening, okay, so then if that's means mass transfer is happening from L phase to G phase. L phase means then X2 will be higher, isn't it? X2 will be higher and X1 will be lower, and Y1 will be higher, Y1 will be lower, and this will be 1. Mean this point 1, in that case this will be your point 1 and this will be point 2. But here, but in case of when it was G phase to L phase, this was point 1, this was point 2. Okay, so but in case of stripping from, means when mass transfer is happening from L phase to G phase, then this will be X2 Y2, this will be point 2, and this will be X1 point 1. Okay, so in this case, that whatever the carbon dioxide content in ethanol, that will be higher. Okay, and it will be much higher than your equilibrium, then only the strip up will, because driving in this case your this will be your liquid phase driving force, okay, and this will be your gas phase driving force, isn't it? This will be your gas phase driving force, and in this case also that same thing will come. This, if you make this material balance based on this y1 minus y2 x1 then L by this. Okay, So this will be, the slope will be same, LS GS same. If you this slope and this, so these are parallel, but it will be below this equilibrium line. So this is my equilibrium line, but here equilibrium line, keep it in mind, this is G phase, means capital Y L. Now when mass transfer will occur from G phase to L phase, then your operating line will be above the equilibrium. And when mass transfer will take place from L phase to G phase, then operating line will be below the equilibrium. And this thing, but equation, all these things will be same if the slope is same. Okay. So this, and from here, if you take the any point, if you take the minus kx ky, it will reach to the here minus kx ky. Okay. So here in the two things are possible. Either if you mass transfer occurs from G phase to L phase, let's take absorption, and L phase to G phase, the stripping. Principles are same, only the operate equilibrium, everything will, material balance, everything will be same, but just there will be one change, the operating line will be above the equilibrium line when mass transfer will happen from G phase to L phase, and below the equilibrium line when mass transfer will happen from L phase to G phase. And here, as we have taken the solid free basis LSGS, so these operating lines will be constant. That means slope will be constant, means it will be linear. So your here M n dash, local overall driving force in the, for the section G, M n dash. So this is the driving force for the gas phase, and I told M n double dash, that will be the local liquid phase, and M n dash slope is minus kx ky. Okay, M dash point meets the equilibrium curve at a point, gives you the interfacial concentration. So whatever the point here, that will give the interfacial concentration. Okay, so here we have understood what thing. With equilibrium curve, we draw another curve, that is operating line. Operating line, what is this? What is the physical meaning of operating? Means what, at what concentration equipment is getting operated. If this is the concentration, and we know that this is up to this equilibrium, so I can go from this point to this will be my driving force. Okay, so the concept of operating line is very important. Okay, so that thing already we have discussed. Okay, from when it will happen from L phase to G phase, then this will be that x2 y2, x1 y1, and this will be rs, and slope will be same, and accordingly this thing will be there. Okay, now let's come to our justification, why we are not taking, why we have taken GSLS. GS means GSLS means capital Y, capital X, and GL means mole, in terms of mole fraction, Y and X. What is advantage that we do? So one thing we have seen, when we consider with that solid free basis GS and capital 1 Y1, that is mole ratio, then my slope between, let's take this point to P and Q, that slope is straight line, there is no change. But now see what will happen if I take the flow rate G. Okay, so if I take the flow rate G, so let's take any point, this envelope one, so G into y entering, L2 into x2 entering equal to G2 into y2 small one mole fraction L into x. So if you take the y minus y2 by x minus x2 equal to L by G, and if you take the whole material balance, then it will come okay. So small y1 minus y2 by x1 minus x2. If you take the extreme 0.1 and 0.2, then this will be your L by G, isn't it? The same thing what way we did this. So here in y and x, I will put this thing 1 x1 y1. So accordingly it will come. Now here if you see this L by G, slope is L by G. Now what will happen? G will keep changing. We have seen this one, because if it is 100 moles, then it will be 98, 95, 92 like this. And it is 100 moles you put it here, it will keep changing, 102, 105, 110 and 110. Just I have given the example. So L and both are changing within this equipment. LS, if this is changing, this means slope is changing. Slope is not constant. The slope is not constant means it won't be the straight line. It will be curved like this. That every point you have to calculate the slope. To get the operating line, you have to calculate the slope at every point, because it will keep changing. So it is difficult. But if you take in terms of mole ratio and LSGS, then once you get these two extreme point, okay, then that slope will be your straight line. This is LS by GS. It is easy. So your calculation will be easy. Later we will see how it will be more convenient to this. But in this case, no, this will be slope. But here, see. But one thing you have to keep it in mind, when you are calculating based on L and G, then you have to draw the equilibrium based on small x, small y. That will be equilibrium curve, and this will be your L by G, that slope curve. But when you want to make this LSGS, then you have to make it capital X, capital Y, that coordinate, that change is required. And corresponding that equilibrium curve will be capital X. So this is the advantage, because if I make the calculation based on solute free basis, then that operating line will be equilibrium. But if you don't, if I do calculation based on total flow rate and corresponding mole fraction L and G, then because of L and G will keep changing, the slope is changing, and it will, then the calculations or determination of designing the equipment will be difficult. Because every point I have to calculate the what is L and G for the material. Every point I have to calculate, then I have to draw this. But when it's LS, then two extreme point, generally it will be known. Okay, so then you can calculate it. So I think now we understand what is the advantage of mole ratio capital Y instead of mole fraction small in designing. That's why we generally consider, okay, the capital Y, capital X based on the solute free basis. So thank you here for your attention. Today, just what we have seen, we have discussed about the counter current mass transfer equipment, and for this one from the material balance we constructed the operating line, and always we have to draw the equilibrium line. If the gap between operating line and equilibrium line is wider, then I will get the better mass transfer because driving force will be better. When mass transfer will happen from G phase to L phase, then operating line will be above the equilibrium line. And when mass transfer will happen from L phase to G phase, then operating line will be below the equilibrium. Remaining all calculations will be same. Also, we have seen that if we make the calculation in terms of mole ratio with solute free basis, then my operating line will be linear. But if you calculate the operating line based on mole fraction and total flow rate, then my operating line will be non-linear, and then each point I have to calculate, and that is difficult job. So calculation of operating line in terms of mole ratio is preferable. Thank you for your attention. Have a nice day.